Okay, I'm resuming recording now, and let me check. Yes, I'm resuming recording. Okay, where is the number of people? Admit all. Okay, all right. Okay, we'll just wait for a while, and then we'll start. Can you ask some questions regarding the tutorial first? Yes. Yeah. Please, Ethan. Yeah. Just type here, and we'll see. In fact, I think I've recorded all the tutorial answers, Ethan. Let me find it for you. Right. Everybody, yeah. So Ethan or everybody, I hope you all have seen this channel, which I recorded a couple of years ago, and it's still useful. In fact, I still use this. Uh, okay. Everybody have access to this channel, this YouTube channel. Okay. Okay, and Ethan, yeah, you can type your questions, and if I have a chance to, I'll answer it during the break. Okay. Yeah, I'm still trying to meet people. I'm just wondering how I can automatically. Hmm, okay. All right. Yep. For the first and second question, is it possible to Ethan, is question first and second question of which tutorial? Chapter 7 is uh okay, let me find what is chapter 7. Is chapter 7 least squares or is it something else? Okay, least squares. For the first and second question, since it's possible to use. I- okay. So I'll answer this question later on in this lecture. Okay. We got 28 people, but unfortunately I have to look at the participation and the waiting room uh, to admit people. All right. We just wait for a little while, so there's no hurry. Okay, right. So I'll just ask again. You guys can see my screen, which is the black screen now, and you can hear me well. Can someone type on the chat, please? Very good. All right. So I'm going to begin on least squares. And we begin with the question, what is the problem of ax equals to b? And by now, I mean, you guys will realize that A is a matrix, X is a vector, column vector, and B is another vector. And this is A, this is X, and this is B. And let's just do something simple. If I have 1, 0, 0, 0, 1, 0, and I have a problem of 2, 1, 0, then guys, may I ask you, what would be x1 and x2b? What values of the x will satisfy this? Anyone? 2 and 1. And the gentleman is of course, or lady is of course correct, because you need to understand how to multiply a matrix with a vector. So I'm going to color code this now. X1 will multiply with the first column, and x2 will multiply with the second column. And actually, what we are doing is x1 multiplying by 100 plus x2 multiplying by the second column 010, and we want it to set it such that it will be equals to 210. And of course, if this, by inspection, you know that I should multiply the first column by 2 and this guy by 1, and therefore actually I have 200 plus 010, and then of course this is equality. The left hand side is equals to the right hand side. So I want you all to look at matrix vector multiplication this way. When a matrix is multiplied by a vector, the first element of this vector is multiplied by the first column. The second element is multiplied by the second column in this idea. So, so are you guys happy with this interpretation of matrix A multiplied by X? Yeah, this is how I want you all to understand matrix vector multiplication. Because once you understand this, then all this notation looks okay. Now, when we can solve, so normally we are given A, X is the unknown, and we are given B. So the problem is to find X. Find x that satisfy. So the question is, of course, and the answer is in this example, the answer is yes. X can be found such that ax is equals to b. So this x is the solution. The x found is a solution of the system of equation. And of course, x is 2 and 1. Now, Hu Qing, in the last lesson, I only covered a little bit because I want to use the time to explain it slowly. You have to watch the video by yourself because if I cover it at the pace, then you might not be able to, or some students may find it difficult to engage. So I'm doing it at a very different pace from the videos that I have put. Hu Qing, did I answer your question? In like today, I will only go through the big idea of least squares. The examinations will cover what is given in the tutorials as well as the recorded lectures. Okay, can. Now, so so to engage guys, I'm going to ask you, why is there a solution? Can someone tell me why is there a solution? Why x can be found such that this? What is the, if you're going to explain it to your friend, what is the correct way to explain it to your friend? Why? In this simple example, you can actually see. Okay, why? Oh, I'm going to draw for you now. Okay, I'm going to draw 100 and 010 for you, and then maybe we can see. And 100 is this vector. This vector, let's call him A1 is 100. The other vector is 010. A2 010. And actually, so this is the x-axis, this is the y-axis, or the horizontal axis, and here's the vertical axis, x, y, and z. So I have only one vector red going here, 100. I have a blue vector going along this y-axis, and no vector going along the vertical axis. But my B, right, is 210. Where is my B? 210. Let's draw him in another color. Let's draw him in cyan. This is 1, this is 2. Here. This is B. 210. So I have A going along here, I have B going along here. And my B is on the floor, on the plane. So the question is, how can I reach B using only A1 and A2? And of course, by inspection, you can say I only move 2 units to the right hand side and 1 unit up along the y-axis, and I can reach B. Clear? So this is actually immediately you can answer the question. Why? Is because B, the answer is B can be formed by linear combinations of columns of A. So this is one way you can say it, but more mathematically you can say it's B is in the column space of A. So the word column space means all linear combinations of the columns of A. So this is the real answer. B lies in the column space of A. So we write here, the column space of A is actually this square. It means that I can reach anywhere on this square. Okay, and this square is the entire floor. Right. So if you have this problem, then okay, fine, you can solve for x. But so now the question is this: when can we not find a solution? Please help to answer this. When can we not find a solution of ax equals to b? Guys, please help. Anybody? Oh, okay, let me admit more students in. Anyone can help? Okay. Inconsistent solution, not within the column space. Very good. So the answer is yes. Answer is when, yes, correct. Inconsistent equation. That's right. That's what you learned in the previous one. Now, if you have more language, then the answer is B is not in the column space of A. So you see in the top, B is in the column space of A. Now we say B is not in the column space of A. So what does not in the column space of A means? Okay, let's use the same example. Let A equals to, what was our previous example? 100 and 010. 100, 010. What is our B now? Just now was 210. Now I make it 213. Then the answer, of course, is if you just look at this, there is no way you can multiply A times any X. There is no way, right? Because no matter what you do, x1 can only be multiplied by column 1. x2 is multiplied by column 2. But the third element of these two columns are 0. So no matter what you do, you can never reach 3. So this is how you can see this as a number, but let's see this as a picture. And the picture is nice, but we can only see 3D. So that's why all our examples is only a vector with 3 elements. Okay, so let's see this picture. Let's take this picture, and now we draw A and B again. All right. And again, the first column, A, I'm going to draw in what color? Pink and blue. Pink, this is the first column. This is A1, so this guy is A1. 100 means going along this direction by 1 unit. And 0 unit along 0 unit here and 0 unit along the vertical. And the other guy, blue. Let's call him A2. And this is A2 and he is 010. And of course now we have our B, which is the cyan color. B is 2 units, 1 unit, and 3 unit up. 1 unit, 2 unit, 3 unit. So you look at this cyan color. He's 2 units along this direction, 1 unit along the y direction. This is x direction, this is y direction, this is z direction. So it's 2, 1, 3. This cyan color vector is sitting on top of this plane. So imagine if this plane is the floor, then you realize that, hey, there's no way we can reach, what do you call it? Because there's no way we can use these two vectors to reach this point in the space. And that's why we can say B is not in the column space of the columns of A. So what is the column space of A? This is the column space of A. It means I can reach any point along here by any linear combination of these two columns. Which Qn is this? Priyanka Kumar, you asked the question. Which question is this? So, okay, maybe since everybody is here now, what I'm going to do is this. This is the least squares lecture. In the least squares lecture, I've already recorded the least squares lecture in this YouTube channel. And you can watch the lectures here and go through the notes, and then you can also do the tutorials here. So instead of repeating everything, I'm going to go through in a very overview fashion such that you see this problem in another way. And this is therefore, useful for you because now you can ask questions as I go through it here. What it means is that you also have to watch the lectures and do the slides. Okay? All right. So now I'm answering the question. When can we not find a solution of x such that ax equals to b? And the answer is when when the system of equation is inconsistent. There is no a that satisfy. There's no x multiplying by columns of a that satisfy this inconsistent equation. The other way is saying b is not in the column space of a, and this is the picture that tells us. See? B is definitely not in the space of A. The space of A is this whole floor here. Okay? And if we want to, it's anywhere along this floor. And B is outside this space. So the word space is actually now very intuitive. All right. So then, of course, the question to you now is, if we have this problem, and this is the least squares problem, what should we do? We do. And the answer is, find x least squares, or sometimes you use x hat, such that what? A times x least squares is equals to, what do you think I will write here? Is it equals to B? Yes, equals to, answer is B hat. And B hat is not equals to B. B is here. B is here, 2, 1, 3. Where is B hat, guys? So the answer is B hat is the nearest point in the column space of A to B. So the question is, if I can only move along this square, the column space of A, where should I land? And then, of course, intuitively in 3D, yeah, everybody can see that this point is B hat. And B hat, you can now know I should move 2 points along here and 1 point up. This is my B hat. So what is my E? The error vector. E. What is? So AX least square is B hat. Therefore, A times X, sorry, A times, how should I put it? Therefore, error, the E vector is B minus B hat. So I'm trying to show you what is E. If I have to reach B, I have to transverse along this line to reach B hat plus E, I will get B. This, this is what this equation is saying. B is equals to B hat plus E. So actually I should write this equation like this. Error E is from this equation. Therefore, E is equals to B hat B minus B hat. Okay. So this is error E. What is error E then? It is 003. So all I need to do is go to B hat plus E. I will get to the vector B. Now, so now the important question is, why? Why E looks, or why E, or not looks, I should say, how E is chosen, satisfying this condition. Anybody? Okay, so I'm asking. Yes, very good. All right. Everybody can see that I have B and I have B hat. Now I'm going to choose another point. Let me use the green. Let us choose another point here on the floor, on the yellow thing. And this point is what? 1, 1. This, let's call him B1. What is B1? I guess it's 1, 1, 0, right? Because I move along one point here and then one point here. This is B1. And then you say, why is B1 a lousier solution than B hat? And then I will now draw for you. Why is it a lousier solution? And what do you see? You see that actually when B is not in B hat, this line is a hypotenuse to a right angle triangle. And you know that the hypotenuse is longer than the side. Okay, so this is the real reason why the error vector is what. So now you can see. Okay, any other point that you have selected will make this error vector longer than E. So what is so special about E relating to this, what do you call that? This yellow square. How is so guess, yeah? How is E chosen? So some of y'all say Wenjie says orthogonal. Yes. And the answer is this. E vector is orthogonal to who, guys? Can you answer me? Try, please. Yeah. Who is E orthogonal to? Yes. And the answer is E is orthogonal to, column space of A. That's one way to answer it. You can also say all the columns of A. What is the column space of A? Is all linear combination of columns of A. So in fact, right, it is very obvious now. See, E is 003. 003 is definitely orthogonal to A1, right? So can you all remember what is orthogonal? How to calculate orthogonality? What does orthogonality means? Yes, very good. So E dot A1, E dot A1 equals to 0. So shows that it is orthogonal. E dot, what about this guy? A2 shows that it's 0. So once I show that it is orthogonal to these two guys, then you say, what about any other guys here in the columns of A? Any linear combination is also orthogonal because E dot alpha A1 plus beta A2 is also equals to E dot alpha A1 plus E dot beta A2, and then now alpha E dot A1 plus beta E dot A2, and then both answer is 0, 0. So therefore, we just show that E is orthogonal to the any linear combinations of A1 and A2. All right. So this is the trick. To find the best B hat, all we need to find is such that B hat is in the column space of A and the error is orthogonal to the column space of A. That's it. So this is least squares. So in these two slides, we have shown why first B, if it is in the column space of A, the solution exists. In the second slide, we show that if if B is not in the column space of A, we find B hat such that if B hat is in the column space of A, and E is an error vector that is orthogonal to the column space of A. Okay, so now let us answer one question. Let us, let us really, find norm of E. What is norm of E? Guys, what is norm of E? Please, 9. So but what does it mean? What does norm of E means? What does norm of E means? What is the answer? It's the length. So in a very simple case, you know that the length is here is 9. Yeah? Sorry, 3. But how do we, what is the equation for norm, guys? Norm E is equals to how would I write this equation? Right? So you guys have to know, I will say norm of E and you have to write the equation in the exam. Try. What I mean, you know that it's 9 because it's very easy number in this example. When the number is not so easy like 213. Yeah? So the norm of E is E dot E square root. Okay? Please don't forget the square root, Andy. What does E dot E means? It's E transpose E square root. So this is the dot product. This is the another way to find the dot product. So another way, the summation of I equals to how many numbers? Let's say 0 to 2. Two numbers of E, I. So this is E0, E1, and E2. So it's square root. So it's square root 0 square plus 0 square plus 3 square. Answer is square root of 9. Answer is 3. So again, when a number is very simple, you don't even need to do this. When a number is not so simple, of course, you have to apply these equations over here. So this is, so I will In the least squares question, I will always ask you, find the solution of the least squares, then find the norm of E. So you need to know this. So the question, of course, now is, in a simple case when you can see the solution, you know, you can find the least squares. But how? So my third slide. Is there a process to find the least squares solution, x least squares? Okay, so let's start. We begin with ax, and then we ask ourselves equals to b. Is there such a solution, right? And we don't know. So what do we do? Now I'm not going to derive the least square solution. The derivation of the least square solution is found in the slides and in my recorded lecture. Today I'm just going to show you what is the least square solution equations and how to use it. So the first thing is left multiply by A transpose. So of course, right? I mean, why find in the videos in the so if I want to multiply, so yeah, I left multiply by A transpose, I get this. Now the question is this, huh? Once I do that, this question mark disappear. This is called the normal equation. Always has a solution. So that's why, although here I don't know whether I can solve for x or not. Here, for sure, I can solve for x. So that's why this question mark become equal. Why? Look at the video lecture. It's called the normal equation. Now, if this matrix A transpose A is invertible, then we are going to, so this is step 1, guys, and step 2. Step 2A. Then we are going to left multiply by A transpose A inverse. So this will become A transpose A inverse A transpose AX. So this the same thing, right? The right hand side, A transpose A inverse A transpose B. So far okay? So this is actually, now of course we can reduce because this guy and this guy are inverse, therefore X is equals to, and this answer is called least squares, A transpose A inverse A transpose B. So this is the famous least squares equation, and there's only 2 steps. First, you left multiply by A transpose, and if you're lucky enough, A transpose A is invertible, that's it. So just now, once one of your colleague asked the question, if A transpose A is not invertible, then so here you realize that infinite solution of x least squares exists. Use Gaussian elimination and solve for x. So what happened is that here A transpose A is not invertible, but you can, you can reduce this by Gaussian elimination because this is a square matrix, or it's not even a square matrix. You don't care. Right? A transpose A is a square matrix, but you can do Gaussian elimination on this, and this vector using Gaussian elimination of your, Professor Deepu's course, you can solve for x. And why? It's because this equality is true. Okay, so have I answered your question? I think the question was given by, let me see, Ethan. So Ethan, yeah, have I answered your question? Yes, okay, can. But now let's have some examples, okay? Let's have some examples. In fact, we are going to do this exact same example again. A1 and A2 that looks like this. Okay, 1 0 0 0 1 0. Okay, let's try. So now I have example. Example A equals to 1 0 0 0 1 0. B equals to 2 1 3. And of course, in this very simple case, you don't even need to do this, right? You can just inspect and you can find the answer. But now let us, use this formula. All right. So anytime when you are not comfortable with what I'm doing, please stop me. Okay. In exams, we are going to ask you to do this. Yeah. All right. Let's see. A is a 3 by 2 matrix. B is a 3 by 1 column vector. So, what is X? Okay, let's try. A transpose A. What is A transpose? A transpose is 1 0 0. That means this column. So I'll draw a different color for you. 1 0 0. So this 1 0 0 is this 1 0 0. What about the second column? 0 1 0. So what is A transpose? A transpose is nothing but taking this tall matrix and flip it onto the side. So the first column become the first row, the second column become the second row. So this is A transpose. So this is a 2 by 3 matrix. A of course is same. 1 0 0 0 1 0. 3 by 2. I have a 2 by 3 matrix, I have a 3 by 2. I will get a 2 by 2 matrix. What does this look like? 1 0 0 times 1 0 0 is 1. 1 0 0 times 0 1 0 is 0. 0 1 0 times 1 0 0 is 0. 0 1 0 times 0 1 0 is 1. So this is A transpose A. Very nice identity matrix because the numbers we have chosen is so simple. All right, so I've drawn this out. So now I want to find the inverse. This is only the A transpose A. To find the inverse, A transpose A inverse equals to, if this matrix is A, B, C, D. A transpose A inverse, guys? Can you all remember? Anybody? So you have to remember this, okay? Let me Google for you. 2 by 2 inverse. Yeah. All right. If A is A, B, C, D, A inverse is, and then I'll write here first, 1 over AD, the diagonal, minus BC, multiplied by the diagonal changes, DA, and the other diagonal becomes inverted. So you need to remember this equation of inverse of 2 by 2. And of course, in this example, it is very easy because implying inverse is equals to AD is 1, 1 over 1, the alternate diagonal is 0. I'm changing this, and then I'm minusing this, and the answer is still the identity. Only for this very special case, Can? Only for the very this special case. But for general case, later on you will realize that you have to be able to use this expression for the inverse. Alright, so now I have done this. What about A transpose B? A transpose B. A transpose is 1, 0, 0, 0, 1, 0. B, 2, 1, 3. Then the answer is 2, 1, 0. No, did I make a mistake? This is 2 by 3. This is 3 by 1. I will definitely get 2 by 1. So in fact, so let's remember how to do this. This first row multiplied by this column to give you this number. Then the second one is the second row multiplied by this to give you this number. So A transpose B is 2, 1. Therefore, now we have x least squares equals to, let's go and pick up our number again. This is A transpose A inverse, which is the identity. A transpose B, which is here. And the answer, of course, is 2, 1. So in this slide, I gone through with you how to use this equation for a complete problem here. Okay, 2, 1, which is the value of x vector. 2 is multiplied by here to reach this point. And the 1 of the second element of x is multiplied by this element to reach this point. So it's this vector plus this vector to reach b hat. Clear, everybody? Okay. Now, let's have another example. So I hope you all are happy now and you all can understand, how to do this for at least a 3 by 2 matrix problem. Okay? Now, let me give you some numbers that you might not like. A1 is 100. A2 is 010. It's very easy. It's very, very easy to see the solution. I'm going to give you a different set of numbers. Okay? And then I'm going to ask you any difference. A 100, the same as the previous A. What about, wait, let me find my example. 110. This is A1 and this is A2. And B is still 213. This is exercise 2. Find x least squares. That's the first question. Is B hat the same as exercise 1? X least squares the same? Why B hat and of exercise 2 and B hat of exercise 1 related? Not why, how? Okay? So so think very hard, guys. All I did was I add 1 here, right? You look. A was 1000010. B was 213. Now all I did was change this guy from 0 to 1. That's it. That's all I changed. Now I ask you these questions. Okay? So let's try together. Let's draw the same picture again. What is the column space of A? What color did I use? Pink and blue. 100. A1. 100. Blue. So now blue is not along this, right? It is here. A2 is 110. It's one along here and one along here. Clear? So just now, the A2 was along this, right? Because this is all 90 degrees. Now, A2 is tilted a little bit, 110. Our problem is still 213. Where's 213? What color did I use? Cyan. 1, 2. 1, 1, 2, 3. Still B. Still at 213. Still above this horizontal plane. And this horizontal plane by now is column space of A. And the A's are these two. So my question to you now, okay, is this. Where would B hat land? In exercise 2. Where is B hat, guys? Anybody? You look, there's only these two columns, right? This column and this column. Any linear of this, any linear combination of this column is on this floor. He will never raise above the floor because there is no values in the third entry, no matter what we do. And you realize that the column space of A is exactly the same as the previous guy, exercise 1, right? Any linear combinations can reach any place on this floor, for sure. Do you have any questions on that? That why did I say that? I mean, if I put this here, I can use this linear combination. As long as it's on the floor, I can use these two columns to reach anywhere on the floor. And if I can reach anywhere on the floor, then the B hat must be what? Guys, look back. Must be the same place, 210. Because we already say that 210 is the nearest position to B if it is on the floor. So let's try. So this is B hat. This is E. And B hat is still 210. E is still 003. So some of you might be thinking, I mean, am I bluffing you? Because now I'm changing the A2, right? Are you sure? Am I sure that B hat will still reach the same place? In fact, this is not a correct argument. B hat, because the column space of A is the same, whether A1 and A2 looks like this or not, he must reach the same place because E must be orthogonal to the column space of A. Never mind, let's try. Okay? Let's try. So how do I try? By now, you all must memorize this equation by heart. A transpose A inverse A transpose B. Right? That's it. And now I have A transpose. What is my A transpose? My A, I just write again, 1, 0, 0, 1, 1, 0. My A transpose, 1, 0, 0, 1, 1, 0. So I've written A transpose and A. So now I'm going to write 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, inverse. And then I'm going to write A transpose 1, 0, 0, 1, 1, 0, B, 2, 1, 3. And if you work it out, so the only difficult thing now is this. So this is 2 by 3. This is 3 by 2. I will get 2 by 2. So 100 times 100 is 1. 100 times 110 is still 1. 110 times 100 is 1. The only difference is 110 times 110 is 2. How about this? 100 times 2 is 2. 110 times 212 is what? 3. So now this is the only inverse I have problem with. A, B, C, D inverse is equals to 1 over AD minus BC. DA minus B minus C. This is the equation. So now AD is 1 over 2. This guy times this 2 minus 1. Change order. 2 and 1 minus 1 and minus 1. 2 and 3. So you realize that the only tricky thing is to get this inverse correct and all these A transpose and things like that correct. Okay. 2 minus 1. 2 minus 1 times 2, 3 is 4 minus 3. 4 minus 3 is 1. Minus 1 times 2 is minus 2 plus 3. So it's 1. Did I get it right? Yes. Wow, the number is so simple. All ones. So 1, 1 is x least squares. So let's try. A times x least squares for exercise 2 is, what is A? A is 1, 0, 0, 1, 1, 0. What is x least square? 1, 1. Answer is 1, 0, 0 times 1. So, okay, I'm going to show you again. This one is this one. This one is the second one plus the second one times 1, 1, 0. So it's the first one times the first column, the second one times the second column. Answer is 2, 1, 0, which is B hat. Clear? So it's very cool, right? I just change a number for A. And of course, then I have to do all these computation just to get my new x of least squares. But interestingly, because in example 1 and 2, both of the examples, the columns of A spans the same space. And since we know in the previous example, the nearest point is this, and we found that yes, regardless of changing the columns, as long as they span the same space, the p hat is the same. Of course, x of least squares is different. Huh? X of least squares now is this 1, 1. Just now was 2, 1. Okay. Any questions, guys? Any? Okay, so in summary, in exercise 1, let's call exercise 1A1 times x1 hat, yeah? The least square solution is equals to b hat. And we now find that in exercise 2, a of exercise 2 times exercise 2's least squares is also the same. And the reason is the columns of A1 spans the same space as columns of A2. Okay? Therefore, E1, the error found in A1 and the error found in A2 are the same. Where's E1? So this is, sorry, E2 now. Let's call him E2. Okay? It's the same. All right. Now, let me, so far, right? I mean, I'm now going to change another number, okay? And exercise 3. Or guys, maybe I will pause now to take any questions. Any? Is it, may I ask some feedback on this? Is it too slow or is okay? Is your understanding okay? Anybody else? Right. Thanks, Aaron. Okay. So if you look at my lectures here versus my lecture in the YouTube, what is the difference? Here, I'm only showing you the mechanics. Yeah. I'm also showing you some interpretation. What's missing? I never prove. Yeah. I didn't prove why, I only appeal to your intuition. I never prove the normal equation. Where's my normal equation? Yeah, I never prove all this. I never prove why we can do this and why this, right? In this course, for you guys, you don't need to prove, right? You guys are using this solution, and then now we are interpreting. You guys need to interpret, right? Okay. Now, I'm going to do one more example. In fact, I have two more examples to do. So anytime, for example, please stop me. Now the numbers will become more complicated. 1, 0, 0. So this is still A1. 1 minus 1, 1. This is A2. So now you see that A2, there's a value here. Okay? There's a value here. B, 1, 1 minus 1. What is x least squares? Okay, so if you ever, I give you A, I give you B, I'm asking you to find AX equals to, is it equal to B? And of course, You just say, let's forget about this, let's forget about whether it's equal or not equal. Let's just apply. And then you immediately say x of least squares is equals to A transpose A inverse A transpose B. Okay, let's immediately just solve for this. All right. So now and then now without, now all you do in the exam is you find A, and then you write what is A transpose, and then immediately you find A transpose A, which is this this matrix 2 by 3 multiplied by 3 by 2. And of course, we have, and the answer is, this is 2 by 3, this is 3 by 2, I will get 2 by 2. So the first row multiplied by first column, 1. The first row multiplied by the first column, second column, still 1. This row multiplied by the second row multiplied by the first column, still 1. This, the second row multiplied by second column, this is interesting. 1 plus minus 1 square is 2. 2 plus 1, so answer is 3. So A transpose A is this 1, 1, 1, 3. Of course, we will need the inverse. Okay, fine. So now A transpose A inverse equals to 1, 1, 1, 3. Now, if you have a calculator, it's nice, but if you don't have, then remember how we do it. It is 1 over this diagonal minus 1, 3 and 1. This diagonal swap, and this one 3, right? Minus 1, minus 1, 1. This is A transpose A inverse. All right, then we have A transpose B. B. What's my B again? 1, 1, minus 1. And then this is 2 by 3. This is 3 by 1. I get 2 by 1. 1, 0, 0 is 1. 1 minus 1. 1 I think answer is minus 1. So this is A transpose B. So I have almost all the pieces, right? I have A transpose A inverse, A transpose B. Therefore, x of least squares is equals to, I get this value, half 3 minus 1 minus 1, 1, 1 and minus 1. Answer is half 3, 3 plus 1 is 4, is it? Yes. Minus 1 minus 1 is minus 2. Answer is 2 and 1. So this is the least squares. 2 and minus 1. The Ethan asked, can we write x least squares as x hat? Yes. Doesn't matter. Okay. Just have to be consistent. All right. Now, what is A x least squares? What is A again? 1, 0, 0. 1 minus 1, 1. What is least squares? 2 and minus 1. So it's 2 multiplied by the first column plus minus 1 multiplied by the second column. And the answer is? The answer will surprise you. Huh? What is the answer? Is 2. 2 minus 1 is 1. 2 times 0 is 0. So it is 1. And this is 0. So it's minus 1. But what was B? 1, 1 minus 1. What is B hat? This is B hat, right? AXLS equals to B hat, right? B hat equals to B. Therefore, E equals to B minus B hat equals to 0, 0, 0. Why? Can you all answer? Do we need to show the full working? No. If you all have a calculator that can do the job, just do the job. So now, why? So remember we started with this question, right? What is least squares? So we already find. The least squares what's the answer again? What was my least squares? 2 and minus 1. Is AX equals to B? Yes. Why? Okay, everybody, can you all try to answer this? Yes. B lies in the column space of A. The system of linear equations is consistent. That's the answer. And we know that because B equals to B hat and E equals to 0. So it is not obvious, right? When we start, it wasn't obvious, right? That AX will be equals to B. It wasn't obvious at all. And using this, we still can find. All right? That's the cool idea. So you can think of the least squares as a very good hammer, can solve a lot of problems. And the answer is why? Because B lies in the column space of A. That's one answer. Or B can be formed by linear combination of A. Right? Third, system of equation is consistent. Not only consistent, not only consistent, yeah, but yeah, consistent is good enough. Okay, fine. All right. Anything else you all want me to do? We are 7:40. We're in an hour into this, and anything else? Really? Okay. All right. So I've given you 3 exercise. Hi, Prof. I have a question regarding the least square slides in slide 3. Each row represents an equation. So Ryan asks. Okay. So the question is this. Each row represents an equation. Then columns are individual vectors, right? All right. So let us use this equation. Okay. 1, 1. Okay. So if I say x1 plus x2 equals to 1. 0x1 minus x2 equals to 1. 0 x1 plus x2 equals to minus 1. Can? Ryan? So I give you three equations. How would you write this? You would look at this and say, I have three equations, and now I can write it as a matrix. And here I call it x1 and x2. And here I put the right hand side, which is 1, 1, minus 1. And I call this the B vector. And now in each row, 1, 1, 1, 1, 0, minus 1, 0, 1. So isn't this A? Isn't this X? And isn't this B? So I could have given you the systems of equations, and you can write it in this form. Ryan, is that clear? Now, the question now is, in Professor Deepu's course, you then immediately what? Use Gaussian elimination, right? To solve. Agree? And then you do until then you write the augmented matrix. 1, 0, 0, 1, minus 1, 1, 1, 1, 1. And then now you, right? You say the first row, 1, 1, 1. The second row is plus, right? So you come 0, minus 1, 1. What do you do? You plus or what? Where's my minus 1? Oh, minus, minus. This is minus. So this second row plus this, sorry, this third row plus this is equals to what? 0 plus 0 plus 0, right? And now what do you have? You already have two pivots. Agree? Two pivots. You have two free variable. No, sorry, you have no free variable and you can solve, right? So now you say minus 1, which is the second variable, times x2 equals to 1, implying x2 equals to minus 1. Then you substitute here into the first row. Therefore, x1 plus x2 equals to 1. And you substitute this into here. X1 equals to 1. Here's minus 2 plus 1, right? Is that my correct answer? 2, 1. Yeah. 2 and minus 1. Okay, Ryan. So can you see in the Gaussian elimination, we began with rows of systems of equations, linear equations, and we solve it by this way. But today, we put it as a matrix and we solve it. So you realize that linear algebra is doing the same thing in different ways, and different ways give you the power to solve it. And in the previous case, we can only solve it when the system of equation is consistent, right? Inconsistent, then we're finished. That's why we move it into this new way of seeing things. Is that clear, Ryan? Did I answer your question? Okay. So that's Ryan's question. Now I will go back to my first page. Now, where's my slide? In this slide 3, remember I told you that AX, I don't know whether it's equals to B. But once I pre-multiply my left and right hand side by A transpose, this question mark become equality. Equality, okay? There is always a X that solve a problem. But I have now a problem. A transpose A may not be invertible. Even if it is not invertible, this is an equality. Okay? The infinite solution question. I'm now going to give you an example of the infinite question. Let's look at this infinite question, infinite solution. Example 4. A is equals to, now I need you all to participate, please. 1, 0, 0. B is still my famous 2, 1, 3. What do you think I will put here in my A2? Example, such that A transpose A inverse does not exist. Guys, what values of columns of A2 should I put such that A transpose A inverse does not exist? Anybody, guys? It must be some, something unique about. Okay, look at look at this example. A1 and A2, what are they? They are not linear combinations of each other, right? I can never form A2 by a linear combination of A1. Look at, okay, let's look at the other A. Okay, look at A. A2 can never be formed by linear combination of A1, right? So Ethan is right. We get 2, 0, 0, just for fun of it. So you realize that, hey, this column and this column, they are linearly combination because 2, 0, 0 is nothing but 2 times the first column. So this column and this column provides the same information. I cannot go anywhere with that. Okay, let's see. Okay, let's try A transpose A. 1, 0, 0, 2, 0, 0. This is A transpose. 1, 0, 0, 2, 0, 0. This is A. Answer is, this is 2 by 3, 3 by 2, 2 by 2. Answer is 1. Second one, first row times first column is 1. First row times second column is 2. Second row times, this is 2. The last one, 2 times 2 is 4. Wow. What's wrong with this matrix? Guys, can you answer the question? What's wrong with A transpose A? He's a square matrix, but what? Square matrix. But what? But what? Why is he not invertible, guys? Because? Why is he not invertible? Yes, the first row, I mean, the determinant is 0, right? 1 times 4 minus 2, minus 2 times 2. So 1, of course, is the determinant equals to 0. That's why he's not invertible. Huh? And yes, and he's also not invertible because the rows are linearly dependent and the columns are linearly dependent. Okay? So the what do you call that? Linearly dependent rows and columns. And why did this arise? Why did this arise? It arises because the original columns of A are linearly dependent, giving rise to A transpose A having linearly dependent rows and columns. Okay. So therefore we are stuck, right? Therefore, X least squares cannot be found by A transpose A inverse A transpose B because does not exist. But we still can find XS. But we can use Gaussian elimination to find. How? So let's try again. We start with A, X, question mark, B, right? And then we say A transpose A, X, no more question mark. No more question mark. Huh? So now, what is A transpose A? What's A transpose A? 1, 2, 2, 4. X1, X2. What is A transpose B? Okay, let's find. A transpose B. What is B? 2, 1, 3. What's 2 by 3, 3 by 1, 2 by 3, 3 by 1, 2 by 1. 2, 4. So far, okay, guys? This is A transpose A. X least squares equals to A transpose B. So this is, again, your tutorial 1, right? What do we do? Gaussian elimination. We take row 2 minus 2 times row 1. We get 1, 2, 1, 2, 2, 2, 4, 4. What do I have? 2, 2, second row minus 2 times the first row. What's the answer, guys? Can you all see? So row 2, 2, row 2 equals to row 2 minus 2 times row 1. Answer is 0, 0, 0. Consistent equations, right? Implying what? What's the implication, guys? What's the implication of this? When we all are solving for this, what does, you guys will have this, right? And say the pink box is the pivot. One pivot. One free variable. Right? So what will happen, guys? What is the solution? Consistent equation and only one pivot, one free. Imply what am I waiting for? Imply what, guys? Please try. Infinite solution. Many, many equations will solve this. Okay, let's try. Let's write this equation down. That's only so easy. It is 1x1, this 1 times x1 plus 2 times x2 equals to 2, right? Therefore, x1 is equals to 2 minus 2x2. And if I say x1, I look at this equation. X1 is here on my left hand side. I need 2 here. Minus, then x2. x2 is free. I write here. So this equation, right? This whole line is this line. Clear? Everybody? Did I lose anybody? Okay. What about the second one? X2 is free, nothing to write. X2 is X2. There's no X2 here, right? 0. Then X2, what should I write? Oh, here is plus. Then here must be minus. Here must be plus 1. Therefore, this guy is called the particular solution. If you read carefully, this is the homogeneous solution. So now let's try. Why? I mean, why this kind of funny thing, Let's ignore this because x2 can be 0. If x2 is 0, this will wipe out. So it's only 2, 0. Remember what's my A? 1, 0, 0. What's my A2? 2, 0, 0. What's my B? 2, 1, 3. That's case 1. Choose x least squares, the first one, to be 2, 0. Right? This is the 2, 0. If there's no x2. What is 2, 0? Times A. Therefore, A times x least squares is equals to 2 times the first column, 2, 0, 0. The second column, 0 times this, I don't care. So I am only using 2, 0, 0. Okay, looks okay. What about I choose another x least squares? Let's be 2, 0. Let's choose another one. Guys, let's choose maybe x2 to be minus 1 plus minus 1 times minus 2 times plus 1. Let's see. This guy would be 2 plus 2. Oh, 2 plus 2, 4. What about 0 minus 1 is minus 1. So the x least squares looks very different, right? One is 2, 0, the other is 4 and minus 1. But what about A? Let's call this the x least squares for example 2. A times x least squares of example 2. It is 1, 0, 0, 2, 0, 0, multiplied by who? 4 and minus 1. 4 times the first column. Ooh. 4, 0, 0, minus 2, 0, 0. The answer is also 4 minus 2 is 2, 0, 0. Okay. So there are infinite solutions, infinite XLS that gives the same X, sorry, that gives the same one, B hat. And then you must be thinking, hey, why is this so, This looks very abstract, very, very abstract. Such a simple thing. But once I draw for you the figure, you would understand. Let's draw the figure of 1, 0, 0 and 2, 0, 0. Okay, so again, we are living in the 3D space. A1 is 1, 0, 0. The blue guy. This is A1. This is A2. Who's A2? 2, 0, 0. A2. Although I've given you two vectors and I allow you to perform linear combination of two vectors, where am I asking you to run around? Any linear combination of these two vectors can only run around where, guys? Come, tell me. Can only run around here, along this line. He cannot even run along the floor, the plane. He's finished. He's just running around here. And where's our B? B was 2, 1, 3. Here's 2. Here's 1. And here is B. B is at 2 units along this direction, 1 unit along this direction, and 3 units along the vertical. Therefore, where is B hat? B hat lies here. Let's sketch the B hat now. So B hat is here, 2, 0, 0. Because he can only run along this line. And the nearest to 213, of course, is trying to minimize this error. He cannot minimize the second element error or the third element error. So what is E and E norm? That's always the exam question. So E is equals to B minus B hat, 213 minus 200. E is 013. Norm of E, E transpose E equals to 0 square plus 1 square plus 3 square. Finish. Is it clear, everybody? So in this last example, example 4, I have, and in the example 4, I have shown you that even though A transpose A inverse does not exist, no problem, because in this equation here, the solution always exists in the normal equation. Okay, can. All right. So I've spoken for almost 1.5 hours now. So may I ask you all, I mean, I think the only time that I will have chance to see some of you, if it is convenient, please turn on your camera and then yeah, we'll spend the next 10 to 15 minutes to have a chit chat and I will answer any questions you may have, please. Yeah. Maybe first I will ask you all some question. Is this type of learning going through at this pace? Is it you know, useful? Is it too slow for you guys? Too fast? Okay. Can. Okay, thank you. Yeah. Yeah. I mean, you see that actually we did a lot of slides. No question about it. Can you see? We did almost like 7, 8 slides and a lot of, you know. What I'll do is I will print this out and if you but you can watch this, yeah? Okay. Right. For the exams, guys. So for the exams, you need to remember this equation and like do it like what I'm doing. For sure. The mechanics. And then you have to interpret what is E, or not interpret, you have to get what is E, the norm of E, you have to get the B hat, and then you have to interpret, you know, like what I have done. Okay? Okay, I'm glad it's useful. Yeah. So So guys, I guess you guys, most of your, in fact, I only see 2 or 3 guys turning on your camera. Yeah, may I request you all to turn on your camera because it's actually very unnerving to speak to you all without seeing who are you. Very unnerving. Yeah. Okay, please. Yeah. And in fact, in many universities, we also hope or expect all the students to turn on their camera, right? And yeah. Total how many questions during the exams? I don't know. I think I only said 2 questions and a few parts. So for my part, one question is on orthogonality and one question is on least squares. Okay? Must be yeah. It's not very fun to speak to a blank screen. You're totally correct. Yeah. Yeah. So it's and in fact when I speak to you all like this and I can see your reaction, it's also very nice because actually in the class, when the students come, we gauge our pace because whether the students are having problem. Yeah. And in fact, nowadays I use Google Clap, and then the students can answer. Okay. Any other questions? I'm very happy to see many of you are here. Uh, it must yeah. For tutorial orthogonality for least squares, why do we need to focus on? Do we only need to focus? Yeah, Aaron, I cannot really answer the. I cannot answer. I cannot give away what we'll ask in the exam. Okay, so but if you understand today's lecture and the last week's lecture, then you can at least answer at least 50% of my question. How's that? Yeah. So if you can understand today's and last week, yeah, you'll be able to answer a large part of my questions. Yeah. Well, but we don't do any proving, right? We don't do any proving. You realize that my full-time students, they would have other kind of problems. Yeah. They would they the questions might be why does why does the normal equations give you the solution, things like that. Okay. Yeah, like you see, I never explain. Yeah, this slide 3, I just jump, I just give you, show you and showing you that this is the way to solve. I never show you why this is true. Okay, but in the recordings I show you, but but maybe I'm not gonna ask you. That's why yeah. How's that? So for your class, we are doing at least some mechanics, and at least you can get the mechanics right. Then yeah, maybe I'll revise something for you, which you must know. Okay, guys, which is A dot B. This is A dot B. A dot B has 3 definitions, right? This is the first definition. Then the second one, which you all are doing, right? So this is A1, A2. Oh, I should not. Okay, let's start with 1. Okay? And the third one, there are 3 ways, right? Remember? A transpose B, B transpose A, only true for real vectors. In your course, you are not studying complex vectors, so A dot B all looks like that. These 3, okay? Can? Yeah. And then what is norm of A? Is equals to. So the norm of A by Pythagoras theorem, remember, is A1 square plus A2 square plus an square root. This is the Pythagoras theorem extension, right? And then this one, shouldn't it look like A transpose A? Yeah. So you all have to, copy this down and memorize it somewhere. In fact, I think you all have allowed 1 page cheat sheet, right? So you all do this and you all memorize or write down some of these equations or examples, and then you all can do this in the exams and use if you find it useful. Ernest, yeah, uh is a matrix orthogonal. Okay, I can only tell you about my questions. I have 2 questions. One is orthogonality and one is least squares. And linear algebra will consist 50%. So it's my part and Professor Dipu's part will consist 50% of the exam. And then 50% will be by Professor. Uh, who taught you all for calculus? Adams, right? Adams Kong. Yeah. Okay. Okay. So remember this. Don't waste your 1 page. Write your 1 page with the important equations like this. And if you all can just write in one example like this, so that if you ever have a chance to do this in the exam, you have some kind of references. Okay. Anything else, guys? Okay, if not, I don't think I have any more materials for you. We have done quite a lot. We have done almost 7 slides worth in this 1.5 hour and you know, at least 1 hour and 40 minutes now. The cheat sheet is double-sided A4, you're right. So you can use both sides of the A4. That's the cheat sheet. So maybe one side will be for linear algebra and the other side for calculus. No? When today's video will be uploaded? I will try to upload it. I mean, if I should stop. I hope. Yeah. Okay. I can pause. Oh, where's my pause and stop? I can stop recording now, right? Okay. I'll stop recording now.